Okay, here's an addition to our treatment of kinematics dealing with gravity. What do we do about gravity? There's a lot of problems where the problem is described and something's happening vertically, and it's assumed that you're under the acceleration of gravity. So for these problems, for freely falling objects where there are no other forces, we just know that it's freely in the air, we have that the acceleration of gravity designated by G is 9.80 meters per second squared. And that 9.80 meters per second squared for Earth's gravity is directed downward towards the center of the Earth. So that is the value of gravity, acceleration of gravity. So how do we use this in our kinematic equations? Well, we're going to have to define a positive direction for us. And I'm going to suggest that you choose the positive direction as your initial velocity direction. So whatever your initial velocity direction is, that's your positive direction, and all other quantities have to be defined in terms of that positive direction. For instance, let's say you're throwing something down. You can define down as your positive direction. And if you do that, your initial velocity will be down, your displacement in that direction will be down, acceleration of gravity will be a positive quantity and down as well. All these things will be defined as your down direction. And that kind of makes sense, because if gravity is pulling things down towards the center of the Earth and you throw something down with some initial velocity, it's going to increase in speed as it's falling down. So it's going to increase, its final velocity will be greater than its initial velocity. Hence, acceleration should be a positive quantity, because it's increasing your velocity. So it all makes sense. So if I define down, then my acceleration will be equal to a positive g, 9.80 meters per second squared, and ball moving down will have a positive velocity. If eventually it's moving up, it will be a negative velocity. Likewise, my displacement in a down direction will be positive, and any displacement up from my initial position would be a negative displacement. We could also define up as positive, and I would again choose my initial velocity direction as determining that that's what's going to happen. So if I'm throwing my initial object in the up direction, then I will define up as positive, and all my other quantities will have to follow suit. So we always know that gravity is pulling down towards the center of the Earth. So if I define up as positive, that automatically makes my acceleration a negative 9.80 meters per second squared. So acceleration will then be a negative g, a negative 9.80 meters per second squared. And my initial velocity will be positive, since I was going up to begin with. But any subsequent velocity will be defined in terms of up as positive and down as being negative. A ball moving up will have a positive velocity and a positive displacement from that point. If it ever comes down below my initial point, then it could have a negative displacement. But we're going to just go with our positive definition as up being positive. Let's try this out in a problem. A student throws a set of keys vertically upward to her sorority sister in a window 4 meters above. The keys are caught 1.5 seconds later by the sister's outstretched hand. With what initial velocity were the keys thrown? All right, so it's assumed, since we're throwing it freely in the air, it's under the acceleration of gravity. Now, since the student is throwing the keys upward to begin with, we're going to choose up as our positive direction. Our displacement then will be 4 meters, because the sister is going to grab it 4 meters higher, and that's in up direction. So our displacement is going to be a positive 4 meters. Acceleration will be a negative 9.80 meters per second squared, because since up is positive and acceleration of gravity is down towards the center of the Earth at 9.8, it's going to be a negative 9.8 in this case, because it's in the negative direction. And that makes intuitive sense, because if I throw something up and acceleration of gravity is working against it, it's going to slow it down, and hence it's going to be a negative acceleration. Time is 1.5 seconds. My initial velocity is what? So I have 3 kinematic variables. We're solving for the 4th. And it looks like I want to use kinematic equation number 4 for this problem. Final velocity was not given, not asked for, not given. Kinematic equation number 4. So we have displacement, delta y is equal to initial velocity times time plus 1/2 acceleration times time squared. We'll solve this for initial velocity, so we'll subtract the 1/2 at squared from both sides and then divide by t. So we have initial velocity is delta y, displacement, minus 1/2 at squared over t. Let's put in our values. Delta y is 4, minus 1/2, 0.5. Acceleration was a negative 9.8. T was 1.5 seconds squared over 1.5. In the numerator, I'm going to have a negative, so that's going to be plus. And when I calculate all that out, I get 10 meters per second. I came up with a positive value, so indeed my initial velocity was a positive 10 meters per second upward. Now here's a question. When I throw these keys upward, or the sorority sister throws these keys upward, will the sister catch them on the way up? Or does she catch them after they've gone up to the maximum height and then on their way down? So is she catching these on the way up or on the way down? How can I determine that? Well, if I can find the final velocity of these keys, I would know. Because if the final velocity of these keys is positive, then they're going in an upward direction, and that's the positive direction. If the final velocity is negative, that means they're on their way down, and that's in the negative direction. So let's calculate the final velocity. What's the velocity of the keys just before they were caught? Well, we can use the kinematic equation number 1 to figure this out. Our final velocity is our initial velocity plus the acceleration times time. Our initial velocity is 10. The acceleration is a negative 9.8, and our time is 1.5 seconds. So this is going to be 10 minus 14.7, so we get a negative 4.68 meters per second. The negative sign for our final velocity means it's on its way down in a negative direction. So it actually went up, reached the apex, and started on its way down. Excellent. Okay, let's try another problem. The ball is thrown directly downward with an initial speed of 8 meters per second from a height of 30 meters. When does the ball strike the ground? So in this case, we're going to define down as positive because that's our initial velocity direction. And if down is positive, the acceleration of gravity will be positive as well, and hence it's going to be increasing our speed as we're falling. So we have our displacement, 30 meters down, is positive. Acceleration of gravity is 9.8 meters per second squared, positive. Our initial speed will be positive, and time is what we want to find. So we have 3 variables in time we want to find. Final velocity is not asked for and not given, so we'll work with these 4 variables here. So we have kinematic equation number 4 again. Displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. In this case, the acceleration is a positive g, which is 9.80 meters per second squared. Putting in our numbers, our displacement is 30 meters, our initial velocity is 8 meters per second, 1/2, g is 9.8, and we have time, that's which we need to solve. We're going to end up with a quadratic equation. We got 4.9 t squared plus 8t minus 30 equals 0. We need to solve this. We have to use the quadratic formula. So if we identify our variables, our a, our constants, our a constant is 4.9, our b constant is 8, and our c is a negative 30. So with a equal to 4.9, b equal to 8, and c equal to negative 30, a quadratic formula for t is going to be negative b plus or minus square root of b squared minus 4ac divided by 2a. Let's put in our values. B is 8, so we're going to have a negative b, negative 8, plus or minus b squared, 64, minus 4 times a was 4.9. C is a negative 30, so in the numerator here under the radical, I'm going to have a negative negative, which will be plus, over 2 times 4.9. So this is a negative 8 plus or minus, and the square root of all that stuff is going to be 25.53. I'm going to get two answers here. If I add the 25.53 divided by 9.8, I'm going to get 1.79 seconds. If I subtract it and divide it by 9.8, I'm going to get a negative 3.42 seconds. Since we don't know how to go back in time yet, we're going to select the positive value, the 1.79 seconds. And so it will take 1.79 seconds for this ball to hit the ground. We can't go negative yet in time. I'm working on it. I need some more volunteers. Every time I get a volunteer to go into my time machine, they go and they never come back. So I need more volunteers to test this out. So if you want to get some extra credit, just let me know and test out my time machine. But for the moment, we don't know how to go back in time. But does this negative answer have any physical significance? Yes, it does. If I'm throwing a ball down at 8 meters per second, and it takes 1.79 seconds to get to the ground, if I reverse this problem in time and go backwards so that the ball goes up to its apex, comes down and crosses my level, and goes down the displacement back down to the ground, that would have been 3.42 seconds previously in the past. In other words, if I launched it from the ground, it went up past my level at 8 meters per second, went up to the apex, momentarily stopped, started to accelerate, past my point at 8 meters per second. That whole process was 3.42 seconds. And then it would reach the ground 1.79 seconds after that. So that's why the mathematics actually give you two answers, because all you gave was a displacement to the ground, and so it was solving for that position at the ground level. So this is my short lecture. Incidentally, we couldn't have done this problem assuming that our final velocity was 0, even though it's hitting the ground and it's stopping, because we can only talk about intervals of time where the acceleration is constant. Once this ball hits the ground, no longer a constant acceleration. The acceleration changes due to the forces of the ground acting on it. So we can only talk about when we release the ball, it's under the acceleration of gravity up to the point where it's just about to contact the ground. Once it contacts the ground, all bets are off. We can't use the kinematic equations, at least for both situations. We can start talking about when it contacts the ground and when it stops with the ground, and talk about that constant acceleration situation, but that's a different problem. So we can only deal with constant acceleration if we're going to use these kinematic equations, these great 5 kinematic equations. Okay. Try getting into the problems and do as many as you can